Hi folks, before we begin the lesson, I just want to make sure that you know all of these standard temperatures. So mark down how many you got correct out of these. Average body temperature is about 26.5 degrees C. So when you actually say, oh, I've got a bit of a temperature, you're actually talking about a fever, so having a higher temperature than 26.5. And usually if it's heading towards 30, you're getting really quite ill. The temperature of the sun's core is about 15 million degrees C. So, it's a temperature that I can't even begin to understand. Boiling water is 100 degrees C, and that's if it's pure water. If there's any impurities in it at all, if there's a little bit of salt or a tiny bit of chlorine in it, that's going to affect the temperature that it boils at. And ice, the temperature that water freezes at, again, is at 0 degrees C if you're talking about pure water. On a hot summer's day, it's about 30 degrees C, and that's a really hot summer's day in the UK. Short and t-shirt weather is about 20 degrees C out when it's outside, which is really lovely and warm. Hottest air temperature recorded on Earth, which was in Death Valley. The temperature went up to 56.7 degrees C. That's going to burn you very, very quickly. Surface of the sun is 6,000 degrees C, and absolute zero, and that's theoretical. If you could actually make temperatures as cold as possible, then it would be minus 273 degrees C. That's known as absolute zero. And you've probably heard of Fahrenheit, which is another unit we can use for measuring temperatures. There's another unit which you probably won't have heard, and most people don't hear about until they get to A level, and that's called Kelvin. So absolute zero is when it's 0 Kelvin or minus 273 degrees C. So note down now on your sheets, what was the score that you got? So far in this unit, we've talked about thermal energy as a way that energy can be stored or transferred. So far in this topic, we've talked about thermal energy or heat as a way that energy can be stored or transferred. In today's lesson, we find out about the 3 different ways that thermal energy can move from one place to another. For example, the way that we get heat from the sun, or how having the radiator in the corner of a room will actually result in the whole room getting hot. Or why it is that if you held a metal spoon in the fire, the end of the spoon will get hot, even though it's not touching the fire itself. There are actually 3 different ways that thermal energy can move or be transferred from one place to another. These are conduction, convection, and radiation. Before we go into the details of how these different methods of heat transfer work, first I want to talk a little bit about some of the general rules about the direction that heat will be transferred. Firstly, heat or thermal energy will always move in the direction of where it's hotter to where it's cooler. This goes against what you'd naturally think. For example, if you think about a glass of water with some ice cubes in it, what most people think is that the ice is making the water go colder. What's actually happening is because the water is warmer than the ice, the heat from the water is moving into the ice cubes and making the ice cubes heat up, and therefore the ice starts to melt. Because the water's losing heat energy to the ice cubes, the temperature of the water overall starts to go down. If you think of it in terms of thermal energy, this means that wherever there's more thermal energy, the energy will move to where there's less thermal energy. So if you think about a room, if you put something that's hot in the room, that hot item is going to keep on cooling down until it gets to room temperature. Similarly, if you put something cool in the room, then it's going to start heating up until it becomes air temperature as well. The only way to get something warmer than air temperature is if you keep on somehow releasing energy. So our bodies, which are about 36.5 degrees C, are constantly losing heat to the environment around it. This means our body's got to use a lot of energy, releasing energy from the food that we eat to keep our core body temperature warm or warmer than room temperature at that 36.5. The idea that everything must become eventually the same temperature as the air around it is really weird, and it's quite confusing because, for example, if I touch this pan, which has been left out all evening as it dries, and I touch this, which is a wooden handle, this pan feels a lot colder than this brush. You need to have quite a long think about why. So my hand is warm, it's about 36.5. This pan is about room temperature, so about 20 degrees. When I touch the pan, the heat from my hand is being transferred along the metal and it's acting up the handle. So my hand is losing heat to the pan really quickly because the metal pan is a really good conductor of heat. So that transfer from my hand into the metal happens really quickly and my hand therefore gets cooler and warms up the pan rather than the pan heating up my hand. The pan is the same temperature as the air around it. This, again, is exactly the same temperature as the room around it, and yet if I touch it, it feels warmer, and that's because I'm losing less heat or thermal energy to the wooden handle here. So that's the difference between an insulator, which is this, something that doesn't transfer heat very well, and a conductive thermal energy, for example, anything made of metal. Metal things feel cooler even though they're actually the same temperature. I'm going to try and prove this idea to you, and ideally I'd like you to try and do this experiment at home. To do it, you need two different items. One of them, that's an insulator, so I've got a sort of bit of cardboard pot, and I've got my metal pan from before, and they need to be things that you've left out, they've been left in the house for a while and therefore should be room temperature. If I touch my metal pan, it feels like it's colder than the pot, although if what I'm saying is true, then both of them should be about the same temperature. You also need 2 bits of ice, and I'm going to put 1 bit of ice on there and another one onto my metal. Now if it's true that if because it feels colder, it is colder, then you'd expect the ice to melt more slowly than the one on the cardboard. It's not quite balancing there. And I want you to see which one melts first. Again, if you can stop the video here, have a go yourself and see which one melts colder. If you don't have ice or you don't have a pot, then you can watch this end bit of the video. But I've got to hold the pot just because the ice is melting and it's flowing all over the place. And you could see I've put them out fresh, and already, if I get the video and show you from the top, over here, that's the one that was kept on the cardboard. Over here, this is the one on the metal, and you can see water is already dripping everywhere because that ice is melting really, really, really quickly. And yet over here, there's virtually no water at all. So the metal, the pan is transferring the heat into the ice. And here, because it's an insulator, the thermal energy is being transferred much more slowly into the ice, and therefore it's melting at a lot slower rate. Both of them are room temperature, or they were room temperature, but now I can feel this pan is getting colder and colder and colder as the thermal energy that was stored in the particles of the pan, that thermal energy is moving into the ice because it's moving from a warmer area to a cooler area.